Hello everyone, Nina this. Welcome to my new video series on linear algebra. In this series, we will cover the fundamental notions of linear algebra. This series is suitable for anyone with a strong understanding of high school math, so no prerequisites are needed. Our aim is to help you understand these concepts and techniques, so that you can apply them to solve problems in a variety of fields. In this video, we will discuss vectors. For the first section of this video, we will talk about the history of linear algebra. I believe that understanding the history of mathematics can help us see why certain mathematical knowledge was created and why it's important for us to learn it. Plus, if we are doing mathematical research, understanding how previous mathematicians introduced those concepts can give us some ideas for our future research. Before 1880, people discovered many essential things about linear algebra, but a general theory had not yet been formulated. In 1888, Peano, an Italian mathematician, introduced the basic notion of vector space, but it was largely ignored until the early 20th century. So, the history of linear algebra doesn't follow its logical order. The notion of vectors was initially introduced in physics, and it means a quantity having both magnitude and direction. In 1687, Newton stated in his Principia that a body acted on by two forces simultaneously would describe the diagonal of a parallelogram in the same time as he would describe the sides by those forces separately. Although he didn't use the concept of vectors, his idea of the parallelogram of forces suggested that forces have both magnitude and direction, and they can be combined or added to produce a new force. The concept of vectors can be traced back to the late 18th and early 19th centuries, when complex numbers were represented using points and directed line segments in the plane. In 1837, Hamilton published a long paper where he defined complex numbers as ordered pairs of real numbers. In that paper, he also expressed his desire to develop a theory of triplets for three-dimensional space. After searching for the triplets for 13 years, Hamilton found quaternions. The quaternions extend the complex numbers, and they are four-dimensional numbers of the form a plus bi plus aj plus dk, where abcd are real numbers, and ijk are quaternion units, satisfying the following multiplication rules. ii equals jj equals kk equals minus 1, and ij is k, jk is I, ki is j, ji is minus k, kj is minus I, ik is minus j. We can use this graph to remember them. In 1846, Hamilton introduced the term scalar and vector. He expressed that quaternion Q equals a plus bi plus aj plus dk as the sum of its scalar part, a, and its vector part, bi plus aj plus dk. This is why he first used the name vector to describe these objects. Now let's look into the concept of vectors. A vector is simply an object that has both magnitude and direction. When we first learned about numbers, we used a number line, and each number would be a point on the line. In a 2D graph, a pair of numbers, xy, can represent a point. Similarly, in a three-dimensional space, a triple of numbers, xyz, is used. While we can visualize a four-dimensional space, we can still represent it using four numbers for a single point, like this: x1, x2, x3, x4. We can apply the same idea to higher dimensions as well. So a point in an n-dimensional space can be represented as x1, x2, up to xn, where n is a positive integer. The n-dimensional space is denoted by r to the n. Take 2 points on a 2D graph. A is a1, a2, and b is b1, b2. In this video, we will call this point of the vector the beginning point, and this point the end point of the vector. The position vector A of point A with respect to the origin O is represented by this vector OA. We can use the same ordered pair A1, A2 to represent the position vector OA. Similarly, the position vector B of point B is represented by this vector OB, B1, B2. The sum of these two vectors, A plus B, is defined as A1 plus B1, A2 plus B2. Let's consider an example. A is 1, 2. B is -2, 1. The first number in each pair indicates a horizontal movement. A negative number means moving to the left, while a positive number means moving to the right. The second number represents a vertical movement. A positive number corresponds to moving up. A negative number represents moving down. To obtain the sum, we start from the origin. We move 1 unit to the right and 2 units up for vector A. Then we move 2 units to the left and 1 unit up for vector B. We end at this point. In conclusion, we move 1 unit to the left and 3 units up to reach the final point. Next, we explore the concept of scalar multiplication of vectors. Again, we will use a 2D graph. If we have a vector u, which is u1, u2, then multiply it by a scalar alpha gives us alpha u equals alpha u1, alpha u2. For example, if u is 1, 3, then 3u is 3, 9. When we multiply a vector by a positive scalar, it simply changes the length of the vector. On the other hand, if we multiply it by a negative scalar, we can observe that its direction is reversed. For example, -u becomes -1, -3, which points in the exact opposite direction of u. Now we can define parallel vectors. Two non-zero vectors, u and v, are considered parallel if there exists a non-zero scalar alpha such that u equals alpha v. If the scalar alpha is positive, u and v have the same direction. If the scalar alpha is negative, u and v have opposite directions. We can see the pictures here. In this example with u equals 1, 3, we just mentioned the concept of vector length. Now let's write down the formula for calculating the length of a vector. The length of a vector, also known as its magnitude, is denoted by the modular sign. In this case, the magnitude of u is the square root of 1 squared plus 3 squared. Does this formula look familiar? It's actually derived from the Pythagorean theorem. The magnitude of a vector is the length of the hypotenuse in this right-angled triangle. The magnitude of the zero vector is 0. It has no direction. We use this to represent it. In a three-dimensional Cartesian coordinate system, unit vectors are denoted as I, j, and k for the x, y, and z directions, respectively. Their position vectors are 1, 0, 0, 0, 1, 0, and 0, 0, 1. For example, the vector A, 1, 2, 3 can also be written as I plus 2j plus 3k. A unit vector is obtained by dividing a vector by its magnitude. For example, if we have a vector v, 2, 1, 3, the unit vector in the same direction as v is denoted as u and can be calculated as u is v divided by its magnitude. 2, 1, 3 divided by square root of 2 squared plus 1 squared plus 3 squared. And then we get 2 over square root of 14, 1 over square root of 14, 3 over square root of 14. Unit vectors are important because they provide a way to represent the direction of a vector without considering its magnitude. Then we move on to the scalar product, also known as the dot product. It's an operation between two vectors that results in a scalar value, and we can use it to measure the relationship between the directions of two vectors. To calculate the scalar product of two vectors, we have this formula for the general case. From this formula, we can see that the scalar product is commutative, that is, u dot v is equal to v dot u. There is an alternative version of the formula. That is, u dot v is equal to the length of u times the length of v times cos theta, where this theta is the angle between these two vectors. We can use it to find the angle between two vectors. We rearrange the above formula and get this. The dot product provides information about how much the two vectors point in the same direction or in opposite directions. If the dot product of two vectors is positive, it means that the vectors have a similar direction. This indicates that the angle between the vectors is acute. If the dot product is zero, it means that the vectors are perpendicular or orthogonal to each other. That means the angle between them is 90 degrees. If the dot product is negative, it indicates that the vectors have opposite directions. The angle between them is obtuse. Finally, we will discuss the cross product. The cross product, also known as the vector product, is an operation between two vectors in three-dimensional space that results in a new vector perpendicular to both input vectors. In other words, it's used to calculate the vector that is perpendicular to the plane formed by the original vectors. To calculate the cross product of two vectors, let's say u is u1, u2, u3, and v is v1, v2, v3. We use the following formula. The direction of the cross product vector follows the right-hand rule. To apply the right-hand rule, point your right index finger in the direction of vector u and your middle finger in the direction of vector v. The resulting cross product vector will be represented by a right thumb pointing in the direction perpendicular to both your index finger and middle finger. There is another way to calculate the cross product, which involves finding the determinant of a 3x3 matrix, so we will leave that for later. The magnitude of the cross product vector can be calculated using this formula, and again, theta is the angle between these two vectors. The cross product is useful in various applications, such as calculating the normal vector to a plane, finding torque in physics, and solving problems in geometry. So that's a brief introduction to vectors. On this channel, I will also update other video series, so the next linear algebra video will be updated after the next video on this channel. If you are interested in learning more about linear algebra, don't forget to subscribe so you won't miss the next episode. Thanks for watching. I will see you in the next video.